Welcome back, students. So, in the last lecture, we had talked about the Fermi energy, okay, and Fermi level. What happens at T is equal to 0 Kelvin, and what happens at T greater than 0 Kelvin. Okay, and then we had given the example of Fermi level in terms of the semiconductor. Intrinsic semiconductor, extrinsic semiconductor, and then we had gone to this band kind of thing. So here what happens is that a band, these are energy bands. Okay, now where near the Fermi level, okay, near the Fermi level, for any atom only, for energy in a particularly in a one-dimensional well also, you will see that the lower energy levels are spaced very distantly. The distance between the energy levels are big. Now when n is high, that is at higher energy levels, gradually at higher energy levels, they become very, very closely packed. Okay, so now we have to calculate say suppose here this n type, say 10 raised to 16 electrons per centimeter cube is doped. 10 raised to 16 electrons per centimeter cube is doped. Now how will we find out that which electron has occupied which level? Okay, how will we find out that? Now in that case, you see here that here again the same thing. So here only one energy level will not do. First thing is that here the probability, here the energy states, that is the density of energy states, is very low near the Fermi level, whereas the number of electrons are more here. That is probability of occupation by the electrons. You see here from this only you will understand that near the Fermi level, the probability of occupation is the most. Right, it's very near the Fermi level, the probability of occupation is most. As we go more away from the Fermi level, that is a more higher energy, the probabilities becomes less. It's very simple. Near the Fermi level, the probability of occupation of the electrons is more, whereas as we go away from the Fermi level, the probability becomes less. So the same thing here, near the Fermi level, the probability of occupation of the electrons is more, whereas as we go higher energy level, the probability becomes less, but the number of energy levels here is less. Number of energy level here is less. Near the Fermi level, the number of energy levels are less. Away from the Fermi level, the number of energy levels are more. Okay, so what do you do here? So we divided it into energy, this small energy levels DE. We divide it into small energy levels DE here. Okay, then we do the calculation. We divide it into small energy levels. Okay, so since why do we do that? Why do we do that? Because see here there are many closely packed quantum states. There are many closely packed. They're closely but densely packed energy level. So you cannot take any one level and do. So we cannot speak of only one. We need DE, a distribution. Again, we always speak of a distribution. Okay, so there are very closely packed energy levels, so we cannot speak of only one. We have to take a range of energy levels, a range of energy levels. Okay, we have to take a range of energy levels and see then what happens. Okay, so what do you do there? Here we have to employ the density of states formula. Here we have to employ the density of states formula. Density of states. Density of states we have done earlier. What are the density of states? Here also you see GE. See here GED. This is the density of states. GED. The total number of phases, the total number of microstates in the energy range E and E plus D. In the energy range E and E plus D, the total number of energy states in the range E and E plus D we have taken. Okay, we calculate the range. So we need this thing actually. Okay, so we actually need this thing here. Okay, we actually need this thing here. So from there also you can see here, from there also you can observe that you see here this GD, I'll write it in short, DOS, density, is proportional to what? E to the power half. And what is the graph? It is like this. It will be like this actually. A saturation kind of thing will come. Means it will be like this. Like this kind of thing. Okay. Okay, so you see here G is like this. Okay, so GE, how does G look like? G looks like this. If I plot GE versus E, G versus E, how does it look like? It looks like this. So what see here at near I mean, this is what point actually? This is near actually the Fermi level, that is near the conduction band. Here the density of states is almost zero. So see here the same thing, what I am talking about. As the energy increases, the density increases. See, the density increases. As the energy increases, density increases. I have done here also. You can see this. You see it in the internet. The hydrogen atom energy level. You see that as the energy level, with the increase in energy, the density increases. The same thing is proved here. Okay, the same thing is proved here. So this depends on the density of states. So as the energy increases, the density of states increases. So at more energy, where the energy is more, energy level, what to say, at higher energy states, that is more densely spaced. That I want to say. I hope you understand this. At higher energy states, the energy states are more densely spaced, and at lower energy states they are very less. The density is less. So here what you have to do? Number of electrons in the energy range, number of electrons in the energy range E and E plus DE, number of electrons in the energy range E and E plus D. This will be what? This will be equal to Fe. That means it will depend on the probability. Okay, it will depend on the probability. It will also depend on the density of states. See, probability here, these are oppositely related. Probability of occupation here is, if you draw the probability versus E, it will be opposite. Probability here is more, density is less, but probability of occupation here is more, because closer to the Fermi level. So here it is it's closer to the Fermi level, na? So just if you just cross the Fermi level, all will come here. Okay, if you just cross the Fermi level, all will come there. So probability is more. Okay, so this will be what? Fe into this GED, that is the density of states. What was the convention I had used about density of states here? This GED, GED. Okay, Fe into GED. You can use EI also, no problem. So this is the number of electrons in the energy range E and E plus DE. Okay. Now I have given a basic idea about this Fermi level and Fermi states in terms of this semiconductor. Now let us come to some mathematical calculations. Free electrons in a metal. Free electrons in a metal. You know, everyone, that metals consist of nothing but free electrons. A huge number of free electrons, conduction electrons. Okay. I mean, electron gas. That's why it's called electron gas. Okay. Now, so here, since there can be maximum one particle per quantum state, the function Fe is the ratio of the number of the quantum state of energy occupied by electrons to a total number of quantum states available in the energy. So from this thing, let us do. So number of particles having energies in the range, number of electrons, that's why I have written this, number of electrons in the energy range E and E plus D. Okay, number of electrons in the range E and E plus D is given by this. Okay, so now let us do this thing, that is so number of electrons is given as NED. Okay, so this will be what? If you substitute Fe, what will you get? This will be GEDE by Fe is what? 1 by e to the power of E minus EF by kBT. E minus EF by kBT plus 1. Okay, E minus EF by kBT plus 1. Now since GED, you see here, see GED, I had written here, what did I write here? GED, for particles having two allowed values of ms, the number of quantum states is 2 times that of equation 1. Okay, so 2 times equation, so this will be what? 8 pi v by h cube square root of 2e m to the 3 by 2. Okay, so let me write it here. So this will be 8 pi v by h cube into 8 pi v by h cube into, did I tell? 8 pi v by h cube into square root of 2 into square root of into m to the power of 3 by 2, m to the power 3 by 2 into square root of 2 into square root of e into de. Okay, so okay, where you can write where V is the volume, where V is the volume of the, you say, the free electron gas in the metal space is volume of the Fermi space, where V is the volume of the Fermi space of the conductor. V is the volume of the Fermi space of the conductor. Okay, now so NEDE will be equal to what? If you write these things, it will be 8 root 2 into pi v by h cube, 8 root 2 into pi v by h cube into m to the power 3 by 2 into e to the power half by e to the power e minus ef by kBt into d. Okay. Acha. Now this is the Fermi-Dirac law of energy distribution of free electrons in the metal. This is the this is say equation number 1. This is say equation number 1. Okay. Acha. So equation 1 is the Fermi-Dirac law of energy distribution. Fermi-Dirac law of energy distribution for free electrons in a metal. Okay. Now we'll do the total number of particles. Okay, total number of particles and total energy at absolute zero. Total number of particles, total energy at absolute zero of temperature. Okay, so total number of particles very high. It's nearly the Avogadro number. Okay. Acha. So how will you calculate? So this n, let's write n. N will be what? N you will do this thing, integration of 0 to infinity n e d e. Okay, this will be what? This will be this all the other things going 8 root 2 into pi v into m to the power 3 by 2 by h cube into 0 to infinity. Okay, e to the power of half by e to the power of e minus ef by kbt into d. Okay, now this thing what will you do? In the 0 to infinity can be written like this: 0 to ef and ef to infinity. Now ef to infinity will be what? 0, because above the Fermi energy there is no occupancy at absolute 0. Above the Fermi energy there is no Fe is what? 0. Below the Fermi energy Fe is 1, but above the Fermi energy Fe is 0. So it has become easy now. So therefore n will be what? 8 root 2 pi v m to the power 3 by 2 by h cube 0 to ef e to the power of half by e. Acha. Now 0 to ef. Acha. Oh, sorry, I have done something wrong here. This will be plus 1. Okay, this will be plus 1. I forgot to write that. See here, this is plus 1. Okay, so here also I didn't write. This will be plus 1. Okay, so I should have written in black pen here. So this is plus 1. Now what? This is Fe. Now Fe is 1. So this will be just simply e to the power half into d. So what will be that? This will be 8 root 2 pi v m to the power 3 by 2 by h cube ef to the power of 3 by 2. That will be the thing. Okay, ef to the power 3 by 2. So here I did again one wrong here. E to the power 3 by 2 by 3 by 2 will be there. Okay, so 2 will go up, 3 will come down. So what you can write like this: n is equal to 8 pi v by 3 into 2m into ef by h square whole to the power 3 by 2. Okay, this will be the value of n. This is the expression. This is the expression, say equation 2. this is the expression of total number of electrons in a metal at absolute zero. Okay, at absolute zero. Okay, now from here only you can find out epsilon Fermi energy. How you can find out? If you do 2 to the power 3 on both sides, what will you get? You will get the epsilon f or EF, Fermi energy, is equal to h square by 2m, okay, into 3n by 8 pi v whole to the power of 2 by 3, okay, where this thing n by v is called as the number of free electrons per unit volume. Okay, so this you can write as h square by 2m into 3 small n by 8 pi into 2 by 3 whole to the power 2 by 3, where small n is equal to capital N by v. Okay, this is the number of free electrons, number of free electrons per unit volume, number of free electrons per unit volume, okay, or free electron density. So this is the thing, this is the very important conclusion. This can come in your exam to find out the Fermi energy, and various problems, MCQs, numericals can come from this. You have to remember this, that EF is equal to h square by 2m 3n by 8 pi whole to the power 2 by 3. Okay, so from here what can you deduce? That the Fermi energy is dependent on nothing, because h is constant, m is constant, h is Planck's constant, m is the mass of the electron, 3 constant, 8 constant, pi constant. It is dependent only on the number density of electrons. It is not dependent on temperature, not dependent on anything. It is only dependent on the number density of electrons. So this is the Fermi density, Fermi energy at absolute zero expression. So it shows that EF okay, EF depends only on concentration of electrons. EF depends only on concentration of electrons. EF depends only on the concentration of electrons, and is totally independent of on the size, totally independent on the size and volume, totally is independent of the size and volume of the conductor. Okay, EF depends only on the concentration of the electrons, that is n, small n, and is totally independent of the size and volume of the conductor. Okay, now comes the next derivation, that is average energy of free electrons, average energy of free electrons in a metal, average energy of free electrons in a metal at 0 Kelvin. Okay, Achha. So how will you do that? Average energy is written as E bar, average. Okay, so average energy is what? Total energy divided by total number of electrons. So total number of electrons is what? N, and total energy is what? 0 to infinity. Now total energy will be what? Total energy, again here the distribution will come, that is N E dE into E. Okay, any d into E. Okay, any d into E, that is the number of electrons in the energy range E and E plus D into each electron contains energy E. So total energy of the electrons in the energy range E and E plus D is what? N into D into E. Now you calculate the do the integration over entire 0 to infinity range. Okay, the number of electrons in the energy range E and E plus D is NED, and each electrons in the energy range have energy E. So total, this is the total, this much is the total energy of the electrons in the energy range E and E plus D. So along the entire infinite range, what it will be? Integration of 0 to infinity NED into E. Now average will be what? Divided by N. So again, now that 0 to 1 by N, so this will be what? 0 to EF, the same thing, E into NE. Okay, I mean NED. Now NED, you have to put the value of NED. Achha, what is NED here? What is NED here? You write it, this is 1 by N integration of 0 to infinity E into NED is what? NED is FE into FE into GE into DE. FE into G into D. Okay, so again, so 0 to EF, E into FE into GE into DE plus EF to infinity E into FE into GE into DE. Okay, now EF, this thing will always give you 0. So only you have to do the integration of this thing. So integration of 0 to EF. Now FE there is what? FE there is 1. So now you have to just put the value of GD there. Now what is GD? GD just you have to put the value of GD. So GD is 8 pi V by H cube. 8 pi V by H cube. M to the power 3 by 2. M to the power 3 by 2 into root 2 into square root of E. That's square root of E, and E is here. So E to the power 3 by 2 into DE. Okay. So this will be what? 8 pi root 2 into V into M to the power 3 by 2 by N into H cube into E to the power 3 by 2. Now the integration will be what? 3 by 2 plus 1, 5 by 2. So 5 by 2, and this will be what? EF to the power of 5 by 2. Okay, so this will be 16 pi root 2 into V M to the power 3 by 2 by 5 into N into H cube into EF to the power 5 by 2. Okay. Acha, now what will you do now? This, acha, let us you can do it as N. You can write this in terms of N. What is N here? N is here 8 pi V by 3 2m EF by H square into 3 by 2. So you have to write it in terms of N. How will you write? So here what do you have? Here you have got EF to the power 3 by 2 and EF. So you write one EF here. EF you keep constant. Okay. So you can write it like this: 4 pi V Okay, you can write like this: 4 pi v by n into 2m to the power of 3 by 2 by h square whole to the power of 3 by 2 into 2 by 5 into ef to the power of 3 by 2. This you can write. Okay. This you can write. So 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 what is this here? This is nothing but n. Okay, this is, you see from here, this is actually n, this thing n. Okay, so you can write it this as okay, let us write here what is n here. N is 8 pi v by 3, 8 pi v by 3 into 2mef by h square whole to the power of 3 by 2. Okay, this is the thing. Achha, now let us see here what happens. This is ef to the power 3 by 2. It's all right. Ef to the power 3 by 2 is there. 2 to the power 3 by 2, is it there? Yes, 2 to the power 3 by 2 is also there. M to the power 3 by 2 is also there. Pi is there. V is there. Acha, 4 4 into acha 2 ef to the power 3 by 2 is there. Acha, 2 to the power 3 by 2 has to be there. Okay, 2 to the power 3 by 2. 2 to the power 3 by 2. Okay, don't make it so complex. You just put the value of n here. This is n. Okay, so E bar is equal to what? E bar is equal to 4 pi v. Okay, 4 pi v into 2m whole to the power of 3 by 2 by h square, মানে h cube into 2 by 5 into ef whole to the power 3 by 2. Okay, divided by n. N I am putting here 8 pi v by 3 into 8 pi v by 3 h square, মানে h cube will be there, and 8 pi v into 2m whole to the power 3 by 2 into ef whole to the power of 3 by 2. Okay, and there is one ef whole to the power 5 by 2 is already there. Ef whole to the power oh acha, there is ef, only ef, sorry, this ef is there, this ef is there only. Okay, so only ef. So from here what will you do? From here now you have to do this 4 2s are 8, so 8 cancels, pi cancels, v cancels. Okay, h cube cancels. Okay, acha, 2m whole to the 3 by 2, 2m whole to the 3 by 2 cancels. Acha, then ef to the 3 by 2, ef to the 3 by 2 cancels. Okay, so what is left now? ER is 3 by 5 into ef. Okay, E bar is 3 by 5 into E bar, that is average energy is 3 by 5 into EF. So this will be, say, equation number 4. So this is also another derivation which can come to you. The average average electron energy is equal to 3/5 of the Fermi energy at absolute zero. Average electron energy is equal to 3/5 of the Fermi energy, 3/5 of the Fermi energy at absolute zero. 3/5 of the Fermi energy at absolute zero. Okay. Now your last topic of the statistical mechanics and last topic of your entire course is Fermi velocity. I don't know how much is probability of this coming in exam, this thing only. I don't think it's very high. And average velocity, average velocity of a free electron at 0 Kelvin. Okay. Now what we can write, half mvf square is equal to EF, half mvf square, Fermi velocity is equal to Fermi energy. This you can write as h square by 2m into what? H square by 2m into h square by 2m into this thing 3 the EF is equal to h square by 2m 3n by 8 pi whole to the 2 by 3. Okay, so h square by 2m Fermi energy 3n by 8 pi whole to the power of 2 by 3. Okay, from equation 3, I think, from equation number 3. Okay, so therefore from here what you can write, Vf is equal to h by m into 3n by 8 pi whole to the power of 1 by 3. Okay, this comes Vf is equal to h by m 3n by 8 pi whole to 1 by 3. Achha, now if V bar is the average speed, V bar is the average speed of the electron, average speed of an electron at 0 Kelvin, then V bar will be what? V bar is equal to 1 by n, n is the number of electrons, 0 to Vf, V, again you will do this thing, distribution function you have to apply. Okay, where NV dV is the number of particles, NV dV is the number of particles within the velocity range, V and V plus dV. Okay, so now epsilon or E is equal to what? Half mv square. Okay, so dE will be what? dE will be equal to mv dV. Okay, again at 0 Kelvin, Fe is equal to 1 if E is less than equal to EF. Okay, therefore what? NE into D will be equal to G into D. Okay, NE into D will be equal to G into D. From here, this equation, we have already taken that it is 0 to EF, Fermi energy. So within that, Fe is 1, so NED is GED. Okay, Acha. So now NED is GED. So this is GED is what? GED is 8 pi V by H cube into square root of 2ME into M into DE. Okay, so therefore here NV dV will be equal to if you do all the calculation, I'm directly writing 8 pi V into M by H whole cube V square into dV. Okay, so therefore V bar, what you can write, V bar is equal to, from here, 1 by N V into NV dV. So we have got already NVDV. So V bar is equal to 1 by n into integration of 0 to Vf into 8 pi V into m by h whole cube into V cube dV. Okay, so this will be 8 pi V by n into m by h whole cube into 8 pi V by n into m by h whole cube into Vf to the power 4 by 4. Okay, so this will be what? This will be 3 by 4. You can write it like this. This you can write like 3 by 4, 3 by 4 into 8 pi by 3 n, that is n by v you are doing. Okay, so this n by v we are doing, so into m by h whole cube into vf to the power 4. I am already taking 4 into account, this 4 is here. Okay, so this thing, so where n by v is equal to small n. Okay, so therefore here vf cube. Okay, again here vf cube, where have we done vf cube? From here vf cube will what? h by m whole cube 3n by 8 pi whole cube. Okay, in the last page, h by m whole cube 3n by 8 pi whole cube. So this will be vf cube will be equal to h by m whole cube into 3n by 8 pi. Okay, this h by m whole cube 3n by 8 pi whole cube, 1 by 3 cube, so 1, so 3n by 8 pi, h by m whole cube 3n by 8 pi, so h by m whole cube 3n by 8 pi. Okay, so v bar, what will be v bar? V bar will be here, V bar will be 3 by 4 into 8 pi by 3n into m by h whole cube into vf cube, মানে vf to the power 4. Okay, vf to the power 4, so vf to the power 4 you can write vf cube into vf. So vf cube will be what? Vf cube will be written h by m whole cube this h by m whole cube 3n by 8 pi, h by m whole cube 3n by 8 pi into vf. Okay, so 3n by 8 pi, this 8 pi to cancel, h by m whole cube cancel, so this becomes 3 by 4 into vf. Okay, v bar is equal to 3 by 4 into vf, this thing. So this is say equation number 5. So at least if you don't do the derivation of this thing, Fermi velocity, you remember this formula at least. The average speed of an electron, the average speed of an electron in a metal, average speed of an electron in a metal is equal to 3 by 4 times the Fermi velocity. Average speed of an electron in a metal is equal to 3 by 4 times the Fermi velocity at absolute zero. Okay, so this is at least you remember this formula. But others, this, that is E is equal to 3 by 5 EF, this derivation is very important. The Fermi energy derivation, the formula and derivation is important. The N, this derivation is important. Everything are important. This how this GD is 8 pi V by H cubed, the root ED, that is density of states, that is very, very important. I have and I have already done this here. Okay, plus I will tell you to do it for 2 dimension and 1 dimension. Okay, this thing you have to this thing. Okay, so you have to do that. So here finishes your statistical mechanics course and the entire course of your the physics course. Okay, I hope you all enjoyed my lecture. Okay, so if possible, if you have enjoyed it, if you have liked my lectures, give a like in my video and subscribe my channel. Okay, and thanks for cooperating with me. A little bit something is left about laser, okay, which I'll do later and post it somewhere. And here after this there is Planck's law of radiation, so generally that doesn't come in the exam. Okay, just you remember that formula. Okay, generally I mean this thing generally not this thing once it came, but in the for the examiner had told us that you just give, if they write, means you have to derive u lambda d lambda is equal to 8 pi hc by lambda to the power 5 into d lambda by e to the power of hc by lambda kbt minus 1. That is, this is the Planck's law of radiation. Planck's law of radiation. So you have already derived this in quantum mechanics. Okay, here from this is what, this is the boson, this photon, na? This is photon. Planck's law is for photon. So from Bose-Einstein statistics also this can be derived. There is a derivation. So in one exam it has been told by the examiner that I mean that is out of syllabus. Okay, so if the students write this formula right, then only they'll give them full marks. But this is, remember, for only this thing. If they give you in quantum mechanics to derive that, then you have to derive that, but not in statistical mechanics. From they write it from Bose-Einstein statistics. Anyway, I'll again verify that later. Okay, if possible later on, maybe I'll give a short lecture for that also. I think it will not be more than 15 minutes. Okay, I'll give one short lecture and send it in YouTube also. I'll do that. Okay, so keep this in mind. Okay, so and study well. After this I'll take 1 or 2 lectures in Zoom for statistical mechanics. So then there you study this. Maybe after 4 or 5 days, next week I'll take one lecture for statistical mechanics in Zoom class. So you study this nicely. Wherever you are facing problem, you tell it to me. Okay, thank you very much.